Hello student, welcome to the second video on the functions review series. In the first video, we studied the definition of functions and the concepts of domain and range and the various ways to represent a function, the numerical way, the graphical way, the analytic way through formulas. And we looked at some properties of functions. And in this video, we will talk about some some important functions that are commonly used in mathematical models. Okay, a quick word about models. A mathematical model is a equation or an inequality, a mathematical formulation to represent or to describe a real world situation. Like the equation, the formula for gravity between two objects is a mathematical model. The equation, you can similarly have a equation to represent the population of a town or the sales of a certain product in a department store, over a period of time, how does it change? All of this can be described through equations and inequality. And it's not that we are going to come up with a new function for every model. Some select group of functions are used, right? With different coefficients. We'll talk about that in this video. Okay. Linear models, the simplest of the kind, comes with straight line. Linear means a line. Okay. And let us review a little bit about line in theory. So the basis is a linear function or a linear model. And what is a linear function? Whose terms are linear. So the degree of that x or the variable should be exactly 1. Okay, no x square, no root x, just x. That means it can be, there will be one x term and a constant term, degree 1 and degree 0. Okay. And a general function can be then written as mx plus b. That m and b come with meaning. Okay. M is the slope, b is the y-intercept. That means in a typical graph, the y-intercept 0b is here. If the equation is y equals mx plus b, and the slope is m, which means at any point, starting with any point from here, if you go 1 unit to the right, you will go m units up. Okay, the ratio of change in y divided by change in x, what we call the slope, is m. All right, let us look at some examples. The line here is y equals 3x minus 2, and that means its slope is 3 and its y-intercept is negative 2. So, and you can see that in the graph, on the y-axis, the line meets at negative 2, right? Now the slope is 3. The meaning of that, what I was saying earlier is this. Let me move the point to this side. That's 0, negative 2, as the point. If I move now, let's say from negative 2 to, from 0 to 1, okay, 1 unit, then we should rise 3 units up. So the point here, this is at the level y equals negative 2, right? So if you go 3 units up, you will be reaching at 1 comma 1. And you can verify the fact that this is 1 comma 1 by plugging in the value of x in the equation. Y is 3x minus 2, right? So if you let x equal to 1, you get y equals to 3 times 1 minus 2, which is 1. So the point will be 1 comma 1, like that. Okay. And here is another concept I wanted to emphasize. A line that you saw here, its slope is positive. Okay, slope is greater than 0, positive, and you see it is tilted to the positive x-axis, more towards the positive x-axis on the right side. If the slope is negative, like this line here, minus 10h plus 20, so its slope is negative 10, right? So as a result, what happens? The line will be tilted towards negative x-axis. So typically, the moment you see a line graphically, you can figure out whether it has positive slope or negative slope. And you might know this already, right? If it is vertical line, exactly 90 degree with x-axis or parallel to y-axis, in that case, the slope is undefined. Okay. And related to slope, one more concept I want to discuss is the slope here represents rate of change. Okay. In what sense? In the sense of the diagram that you drew earlier. From the y-intercept here at 0, negative 2, if you go 1 unit, if the change in x is 1 unit, then the change in the value of the function, right? The change in y is the change in value of the function. That is 3 units. So the 3 divided by 1 is giving you the rate of change of y with respect to x. So the rate of change is 3. Slope of a line is the rate of change. This idea is important because very soon we will be studying not linear, right? Quadratic, cubic, higher degree polynomials, or other functions like trigonometric functions and logarithmic functions. And there it is not going to be a constant slope. For a straight line, the slope is constant, by the way. Constant slope. Another idea you want to remember. That is for a line. But for a general function, the slope may not be constant. But at every point when you calculate the slope, it is giving you the rate of change at that point. Okay, so that's idea about slope is important. In calculus, if you are going to be either directly studying calculus or using the ideas of calculus, this rate of change is what is called the derivative there. Okay, so in the case of a straight line, it turns out that derivative is the slope of that line, which is constant. Okay. Now, linear models are the simplest models, as we say, but not every real world situation can be modeled by linear functions, right? We need more complex ones. So what is the general goal? A general purpose is you want to find a curve, what I have highlighted in green color here. You want to find a curve that will fit the data that you have, right? May not be a straight line, may not be linear, but whatever is closest, you want to use that. That process is called curve fitting or regression, if you have heard the word. And if you heard the terminology linear regression, in textbooks or in other literature, linear regression is the process of finding a linear, curve to fit a data. But then you can have regressions of every other type, right? The question that I have written here is what we ask. If the linear curve is not a good fit for a data, we have to look for, and the answer is, we look for other models. Okay. in which direction. The first we talk about is stay with the polynomials, but increase the degree. Linear is degree 1. No, degree 1 is linear. If that is not a good fit, you can try degree 2, right? And that will be quadratic. And you can try degree 3, that is cubic, and so on, which is what we will see now. A general polynomial starts with some degree n, and will have the successive terms, some of them may be missing. And at the least, you'll have a constant term. Okay. These numbers that are in front of variables will be called coefficients. The numbers that the variables are raised to the power are called exponents. Okay. Now, for a polynomial, the exponents are going to be these positive integers, starting with that n and then n minus 1, so on till 0, x to the 0, which is constant. So there is no, not much variation there in terms of, possibilities. Whereas the coefficients can be any real number, right? And they play an important role. Both the things, okay? The exponent and the coefficients play an important role. The exponent is related to the concept of degree, and that will be the largest degree. If you look at the polynomial example given here, 6 is the highest exponent, right? So the degree of that polynomial is 6. Okay, that is related to exponent. And that term which has that highest degree is called the leading term. Okay, so I'll erase some stuffs here and rewrite. In this example polynomial here, leading term is that 2x to the 6, the highest degree term. And in that term, 6 is the degree of the polynomial. And there is another number, right? What is in front of x, the coefficient. That is called leading coefficient. Is 6. Okay. The leading term, the leading coefficient is a important parameter for a polynomial. It has significance, as we will see now. Okay. First, let's talk about the linear and the quadratic general forms. Okay. In a quadratic expression, we have already discussed linear. In a quadratic, this a is the leading term, leading coefficient. Okay. So let's see what is its role. If your leading coefficient is negative, there are a number of things to discuss here. First, let us look at some of them. Okay. I'll use highlighter here. If the leading coefficient is negative, you see the curve is facing down. And if the leading coefficient is positive, it's 1 here, okay, on the left side, then it is facing up. That is one significance. The other significance is it tells you how narrow the how stretched the graph is. Here it is 2, right? So the graph is stretched. You can see that it is more steeper compared to the one on the left, where the leading coefficient is 1. Okay, that is one idea. Now we're done with linear leading coefficient. Another idea I want to discuss is what are these parabolas compared to the standard parabola. Okay, in the standard position, the parabola would have been this: y equals x square. Okay, and the parabolas that you see here are some kind of shifts and stretches of that parabola. Right? You start with that, you move it left, move it up, or you reflect it on x-axis, and then move it You can start with this parent graph. You might remember this idea, the transformations of a graph, and obtain these other graphs, right? When you do that graphically, analytically, what happens? The x square gets converted to this new curves, from x square, you make it negative 2x square, and then you might be doing negative 2, then x. I'm just giving an example. Okay. Maybe you might make it x minus 3 over 2, let's say, squared, something like that. Okay, it may not be exactly what is done in this example here. Then you are modifying this x here, so which is shifting horizontally. Then you might want to add something which will be shifting vertically, all of that. So a general curve, what I'm getting at is, whenever you have a general polynomial, ax square plus bx plus c for quadratic, it represents a shift or stretch or some transformation of the parent graph, which is y equals x square. The same thing with higher degree polynomials. Okay, I'll talk about that here. If you see the middle diagram or the left one here is a cubic polynomial, right? And how is this obtained? This is obtained by taking the basic cubic polynomial, which is y equals x cubed, and that's the graph. And now squeeze it, stretch it, move it, and you get this graph. Okay, the one that is here, you get that. And that will be a general shape of a cubic polynomial. Similarly, a general shape of a degree 4 polynomial and degree 5 polynomial. Okay, clear all those concepts? Move on to the next idea. What do you observe? I want you to count something. Okay, this is a cubic polynomial. I'll also draw the quadratic here. The parabola quadratic looked like this, right? This was degree 2. Okay, ax square plus bx plus c type. There is one point where the turning took place. It was one minimum point if it is facing up. Let us look at cubic polynomial. There is one peak here and one low point here. 2, right? Look at the degree 4. There is one peak, one top, 3 of them, right? 3. And then 1, 2, 3, 4. Highs or lows, 4 of them, and that's degree 5 polynomial. Okay, that's one way to. Sometimes you will be asked, this is the graph of a polynomial, what is the degree of the polynomial? You can count. If the number of highs and lows is n, the degree of the polynomial is n plus 1, right? You would observe that pattern. But one thing you have to be careful is equal to that or more. Sometimes it could be more, okay, but at least 5. Like I would say, if I look at this graph, I would say the degree, okay, is at least 5. Okay, similarly in other cases, it could be more. There is like more story and more understanding behind how to know the exact area. We don't get into that, but what I'm saying here is the minimum degree. Okay, and then another concept I want to discuss here before we move on is the concept of zeros. Okay, which is, if you look at the leftmost diagram, I'm going to now erase the previous work. Okay, so I can talk about zeros. If you look at the diagram on the left, it intersects the curve at only one point, right? That's the zero of that polynomial. Okay. Whereas here, if you zoom in, you will see that it intersects here and here also, and again here. So there are 4 zeros here in total. Okay. And in this case, there happens to be only 1 0. And the one that you see in the middle here actually is the maximum possible number of zeros, because the degree of that polynomial is 4, right? It will have at most 4 zeros. But it can have less than that. Like here, this cubic polynomial has only 1 0. This is a degree 5 polynomial and it has only 1 0. That is possible. Okay. But you cannot have more than 5 zeros for degree 5. Another idea to keep in mind. Moving on. We earlier talked about, what if the linear model is not the good fit. And here is an example. If you look at this set of points, if you try to fit them in a straight line, it's not going to be a good one, right? You are going to be off here, not a good approximation. So what would you do? It seems a quadratic function like this. Now, that's it. You can use a calculator to plot those points and then ask the calculator to give you the formula that fits. Okay. Turns out this is the formula that is the best fit. And as you can see, it is degree 2, right? It's a quadratic polynomial. Hence, the graph would be like this, and you can see it has the parabolic shape. Okay. So higher order models, beyond linear. Next, we'll talk about these power functions and some general properties. In the previous video, we have already seen the concept of even and odd functions. Remember that? Okay. Here we are going to look at the general properties. If you go to x to the 4, x to the 5, 6, and so on, general power functions. And these diagrams will tell you a lot. By the way, not only like integer powers, which is the first case, we will also look at other powers. Okay. Now let's first do the integer powers. When it is 1, that's the linear function, y equals x, the straight line through the origin. If it is x squared, that's the parabola shape. X cube has this, inverted S shape or whatever you call it, that shape. And then degree 4 is again looking like a parabola, but a little bit more flat around the origin. Degree 5 again looks like the cubed, but again more flat between -1 and 1. And that is the pattern that will continue. Every even power will look like x squared. Every odd power will look like x cubed. Okay. So that is a general behavior of all power functions. Yeah, that's what we are discussing here. The shape of y equals x is a line. Y equals x squared is a parabola. In general, x to the n for even function will look like y equals x squared. And for odd powers, it will look like x cubed. Okay. And here is a condensed, graphs in a single x and y axis for odd and even, and you can see the pattern. Okay, odd powers, even powers. Okay, that is about power functions with positive integer exponents. Second case, what if the exponent is a fraction? Okay, so some things here like x to the half is under root of x. X to the 1/3, laws of exponents, right, is cube root of x, and so on. So they end up becoming root functions. When the power is a fraction, these are root functions. Okay. This is square root function. And root functions again have some interesting properties. Okay. In the power functions previously, you noticed that for even powers, the output is always positive. Whereas for odd powers, the output could be positive for positive, negative for negative, right? That has its effect on the root functions also. Now, if you take the root of an even root, like square root or fourth root or sixth root, you don't have the negative side on the domain. Why? Because you cannot define square root of -1 or any other negative number. Hence, your domain is only from 0 to infinity. That's what is being discussed. Whereas, if you take an odd root, like cube root of x, the cubes had both positive and negative values, right? So the cube roots are defined for both positive and negative. Okay. And finally, one more thing you would have already observed, but I'm just repeating here. Note the relation between the graph of y equals x squared and the graph of y equals under root of x. Okay. Actually, the under root of x would be only the above one, this one. Y equals under root of x. And if you continue below, that will be y equals negative under root of x. Look at the relation between these two graphs. Okay. You could take that parabola and rotate it 90 degrees, and you get the horizontal parabola, which is the root function. Okay. Similarly, you might have observed the cube root function here. And what was the cube function? The cube function x cubed was this, right? So again, you can see you could take the x cubed function and what do you have to do? You have to flip it and rotate it. You would get this. They have the same shape. What I'm trying to say is, okay, they have the same shape, but what was y-axis earlier is now x-axis. You know, this idea is related to what we call inverse functions. Okay, when two functions are inverse of each other, you see this property. The role that y-axis plays in the original function would be played by x-axis in the inverse function. Root x is the inverse of x squared. Cube root x is the inverse of x cubed, and so on. Okay. Next, if the exponent is negative, say all of these are power functions. Okay. Integer exponent, fractional exponent, now negative exponents. Now, according to laws of exponents, if you raise x to the -1, that is 1 over x. Now, interesting things happen, because when you do 1 over x, when you get x gets closer to 0, 1 over x becomes very large. So it goes to infinity. And similarly, on the negative side also, when it gets closer to 0, it goes to negative infinity. Whereas when you take large values of x, 1 over x goes to 0. It gets smaller and smaller. So we'll get a number of things here. Okay, I will say the coordinate axes are asymptotes. Both the x-axis and y-axis are asymptotes here, but for different reasons. Okay, and those reasons I'm going to write here like this. As x goes to infinity, that is a way to write for large values of x. Okay, 1 over x goes to 0, so that becomes asymptotic there. It gets closer and closer. And as x goes to 0, 1 over x goes to infinity in very simple terms. Okay, there is the thing about going to 0 from the right and from the left. I'm not getting into complication, but when I say 1 over x goes to infinity, I mean it becomes larger and larger here. And that is where you get this asymptote on the y-axis. Okay. And this shape that you see here is called a hyperbola. Okay. You might want to note down the name. Like y equals x squared. That graph is called parabola. This shape, the x shape, is called hyperbola. Okay. So here is an example in real world, on the Boyle's law that is used in physics and chemistry. It talks about the relation between volume and pressure of a gas. Okay. It turns out they have this inverse relation, okay, or reciprocal relation. And what does that mean? If the pressure decreases, the volume will increase, it will expand. But when you look at the right hand side, when you look at the graph, you will see only the right side of the hyperbola, because this is a real world problem, right? So it doesn't make sense to have negative volume or negative pressure. You see, even when you apply mathematical models, you have to be careful. Sometimes you don't look at the whole purely mathematical part. Okay, you look at the real world restrictions and you restrict your domain. You look at only the positive values here. Okay. Similarly, if you have power -2 instead of -1, you would get like 1 over x square function, like y equals 1 over x square. We just want to do a very brief study. What would the graph look like? First of all, it should look something similar to 1 over x, because why not? The same idea, right? When x is large, 1 over x square will be small. When x is close to 0, 1 over x square will be large, with a small difference, and that is, now whether x is positive or negative, x square will be positive. Hence, 1 over x square will only go to plus infinity. Okay. So it's the similar to hyperbola on this side, but on the other side, it's instead of this, it's the reflection, because now it is an even function. Okay, not an odd function. Okay. A generalization of the reciprocal functions, one step further, is rational functions. What is a rational function? T of x over q of x. In general, we say, okay, a ratio, right? From the word ratio comes the rational functions. Numerator and denominator are polynomials. Let us look at the general definition and some examples, okay? And you see the first example here, the same hyperbola. So the ratio functions are the reciprocal functions were a special example of the rational function. Okay, but a general rational function may not have the numerator only one. That itself could be a different polynomial. Now the graph would look a little bit more complicated, and I will explain the general possibilities with a simple example. Okay. This is an illustrative example, does not cover all possible cases. Okay, I will try to cover as many possible concepts, as many as possible concepts with this example. This is a rational function where the numerator is that and the denominator is this quadratic function. A couple of things I want you to note. Look at this x square minus 4. When you set it equal to 0, you get x square equals 4 and x equals plus minus 2, right? What is written here? Those are zeros of the denominator. And what do you see? At 2 and minus 2, there are asymptotes, right? Because the denominator becomes 0 at 2 and minus 2. 2 square minus 4 will be 0, right? The denominator becomes 0. So when denominator is getting close to 0, the values of the function will go to infinity. So you get this vertical asymptotes. One thing. And then second thing you have to observe here is this turnings. Okay. where it is, there is this quadratic, the parabolic thing going on both sides, which makes sense because the numerator is degree 4, denominator is degree 2. If you divide, what remains is degree 2, right? And that should be like the parabola. And in fact, actually, if you notice each component here, there are 3 components in this graph, and each component is some variation of a parabola, right? Which makes sense in terms of the given degrees. What is not obvious here in the graph is if there is a 0 here. This is too close to take a call. Does it touch there? To me, it looks like it does not, and I'll tell you how. When you plug in x equal to 0 here, evaluate f of 0. Okay, you'll get 1 over 0 minus 4, which is minus 1 over 4. So in fact, the coordinate here is, at the origin, it's not touching the origin, it's a little bit below. At 0, the value is negative 1 over 4. Okay, so it means this function does not have a 0 and no zeros. So it does not intersect the x-axis anywhere. Okay. All right. Now, algebraic functions. What are they? We talked about linear, then polynomial, then power functions, in which we looked at varieties, root functions, and then reciprocal functions, and then the generalization was rational functions. We're not satisfied. We want to do more. Now what you want to do is take the root of not just x, but a polynomial which involves x. Let's say something like this. If you start doing this kind of manipulations, the general category would be called algebraic functions. Okay. So here is a formal definition. You construct that polynomial using addition, subtraction, multiplication, division, taking roots. Okay. And these are examples: under root x square plus 1. And here is a rational like function, but it's not rational because the denominator is not a polynomial. But in general, it is an algebraic function. Okay. Everything comes from polynomials, which are either taken the square root or raised to some power and so on. Combinations of polynomials. Okay. Basic thing, starting with polynomials. This is the important point. Starting with polynomials. Those will be algebraic functions. Here is an example, famous example of an algebraic function, which is the equation of, given by the theory of relativity. The mass of a particle is given in terms of the speed of the particle like this. Okay. And it's an algebraic function. The question then becomes, are there functions which are not algebraic? And the answer is in the last row here that you find. Functions that are not algebraic are called transcendental. Okay. Like the numbers that are not real numbers are called irrational numbers. Right? Sorry, numbers that are not rational numbers are called irrational. So the numbers that are functions that are not algebraic are transcendental. Some examples are trigonometric, exponential, logarithmic. We will be doing a brief review of those functions as well. Okay. Which is where we will be starting. I think I will make one more video in which I will review those 3: trigonometric, exponential, and logarithmic functions. Okay. Thank you for staying with me. As I've been saying, this is important. It is important that we review the basic ideas and terminologies and things that we do with functions before you do this intermediate level course in mathematics, because you will come up with these functions and these ideas again and again, and you should not be struggling there. Okay. Thank you for watching. I'll see you in the next video.